sexy. I'm software engineer at Deutsche Bank in London, and I would like to talk about some optimization problems which are linked to portfolio management. When we talk about portfolio, I mean portfolio of some assets. Optimization problems is one of the core class of problems in the financial world. So the three big peaks we're going to touch today are called, the first one, it's going to be slides, it's called the asset pricing theory. It's a theoretical approach to how you price any sort of financial activity. The second one will be more specific to the portfolio. It's how you deal with the portfolio of assets. Say equities, say bonds, say whatever you have. A portfolio in which you have invested, in which you have to manage, somehow manage the risk versus returns of those portfolios. So obviously you want to invest in something that brings money back. At the same time, we all kind of know that if you invest in something, there is also a risk component attached. So you need to balance the two, the returns and the risk. So that's the peak number 2. And peak number 3, which probably might be for you guys more interesting, is actually software type of thing. It's a conic programming. It's a special type of programming. Maybe you know the linear programming. Maybe you know the quadratic programming. Conic programming is like an extensive, vast class of programs which you can nicely code up and solve in the software packages. For these software packages, I'm going to use one very simple, open-sourced Python CVXOPT package, which has a nice documentation. But again, we're not going to go up there. We'll just go do some examples. Okay? So that's the plan. That's the 3 parts of the talk. And for the third part, I will have this Google CoCalc notebook, which we go through. Okay? So starting from the asset pricing theory, I would like to consider a very toy example, of a financial institution. Every single one of you is a financial institution because obviously you do have some income, right? And obviously you do some spending or investing of it. So let's consider these two types of guys. One, we call him consumer, and the other one, we call him investor. Let's start with the consumer one. And let's start with the model that has only 2 time periods, today and tomorrow. No future, no past, today and tomorrow. It's a very simple sandbox example. So E over here, it's not that number E, it's just simply E coming from the word earnings. So it's some income a person has today. And small index T over here and over here represents the timeline. We actually have 2 points on the timeline, T and T plus 1. So a consumer consumes C, everything that he or she earns, E. So C equal to E, either today and also tomorrow. Consumer is a very simpleton. Whatever he earns, he goes buys ice cream for the whole amount of money and consumes that ice cream and feels happy. Now, the investor is another person. Investor thinks a little bit about tomorrow, and investor thinks, or maybe I should not consume everything, E or T. Maybe I should take a little portion of that and invest it into some asset. And now we go to the top part of the screen. Suppose we have some, whatever it is, some thing into which you can invest. And that thing costs some price today. So you can go to a shop and buy it, or go to a market and buy it. And you expect that tomorrow that asset will bring you X. Now, why this is X and that is P? Oh, because P is the price you know, while X is what they call random variable, meaning it might be big, it might be small, we don't know yet. We will know tomorrow, but we are living now in today. Okay? So, I would like to buy capital N copies of this asset. Again, I'm not saying that capital N is an integer. It can be some real number. Well, the true natural markets, of course, capital N is kind of an integer. You cannot buy any any real variable. But let's not think about these details for a while. So my earnings today, investors, sorry, not mine, minus n copies spent on that price P. That's consumption for today. Consumption for tomorrow, again, we have only one time period. So we got whatever earnings we got tomorrow, and we realized payoff, realized money from that asset. Okay? Now we would like to compare these two guys, consumer and investor. We're going to compare them, like which of these two strategies is better. Well, it depends on how we define better, right? Better is defined by some sort of like, it's called utility here, but you can say it's a satisfaction function, happiness function. All similar terms can be used, right? So depending on my consumption, C, there is a certain function which is, the value of that function gives the happiness followed that consumption. Like 1 ice cream, happy, 2 ice cream, more happy, 3 ice creams, even more happy. What happens when I consume 100 ice creams? 100 ice creams, is it more happy than 99 ice creams?
It's about the same happy as 99 ice creams.
A little bit more, but not the same difference as between 1 ice cream and 2 ice creams, right? So what we can say about this function u in general, perhaps this function u is what they call in calculus concave down. That's why you need calculus in order to do financial math. So this is u, this is c. So it's a function of the amount you have consumed. Well, you can try modeling it by some sort of a logarithmic function or maybe some other function like that. But the point is, if your marginal consumption for the small values of c is bigger than your marginal consumption. By marginal consumption, I mean the difference between you have here some 2 levels of consumption over here and 2 levels of consumption over here with the same difference between them. Over here, the marginal, this difference between the values is much smaller than here, right? So people who know calculus, can you tell me what that means in terms of the derivative of the function u? Derivative of that function is decreasing. Okay, good. Let's remember that. Thank you. Right, now, here is my first optimization, main optimization problem. I would like to combine together the utility, the happiness function of consuming something today, plus happiness from consuming something tomorrow. I would like to add these two terms in one single utility function on the bottom. Maybe I'll just scroll it up like that. All right? Now, this piece I know today. The piece tomorrow, as we discussed, there is a random variable x over there, right? That's why this expression, u of c of t plus 1, because c of t plus 1 depends on x t plus 1, so that thing is actually not known for certain. It's a random variable, a function of the random variable, which is also a random variable. Okay? So, I'm putting here the e symbol for the expected value of that random value, expectation of that random value. Right? So you need to know a little bit about probability theory. I hope at least you understand the concept of it's kind of like the average value of average expected value of that random variable. Okay, what is this coefficient beta here? Well, this coefficient beta is there because of the human nature. Because every human thinks about like, okay, fine, tomorrow, yeah, expected values, yeah, probability theory, but I prefer today. Today is somehow more reliable. I can touch it, it's today. Tomorrow, God knows what happens. So this is a kind of like a discounting coefficient coming from every person's human nature. So altogether, this expression depends on a certain choice that we made. Let me recall, what choice? The choice of the investor is how many copies of this asset that investor purchased. So this big function, utility function, depends on n. And the question we can ask over here, let's maximize it. Maximize it, what do we mean by maximize it? We mean by find the best parameter capital N, which leads to this expression giving the topmost value possible. So our variable here is capital N. Now, again, when we do a little bit of calculus, we know that if you have a function of one variable, if you want to maximize that, find the maximum of that function, one can do something like differentiate and find the zero of the derivative, right? I hope they explained that in the calculus class. So I have it here on the very last, on the bottom line. So I'm differentiating that utility function with respect to n. Let's see what will happen. So when I differentiate this with respect to, I got some derivative of our function u. Remember a comment about this derivative. Plus beta. The function of taking averages is, let's assume that it commutes with the derivative. So derivative can be applied to whatever is inside. All right, so if I differentiate this, I'll get something like that. And if I solve this equation, say, solve this equation for what? Solve this equation for p. The solution will be on my next slide. Oops. That's what I get. From the condition that we need to maximize u, I got the following fancy equation. So the price, today's price, which I know, is equal to some expected value of a certain cumbersome expression in which my asset price tomorrow is involved, but also this coefficient is involved. This coefficient I will call m and give it a name, stochastic discount factor. Why m? Well, because it's a magical coefficient. What's so magical about it? So if I rewrite my formula over here in this way, so this very equation, the guys who, the theorists of the asset pricing theory, they call it the asset pricing equation. It's like the key equation of the asset pricing. And what they say is, the meaning of this equation is that the price today can be, and when they say price today, they mean the fair price today. There is a lot of discussion about whether markets are fair or unfair, what is the fair price, but let's not go into the very details. The fair price today, in a good market, must be connected to the asset price tomorrow via the expectation of the product of that asset in the stochastic discount factor. And in our toy example, we had just one asset. We considered just one asset. But expanding that, you can consider many different assets, just like in the real world. The equation then will have the same stochastic discount factor for all of the assets. So the big pricing, asset pricing equation says that you can imagine here that x and p, they correspond to any particular stock, bond, option available, while the stochastic discount factor is the same for all of them. So this stochastic discount factor in some form represents the whole market and the collection of all the thoughts and happiness functions, discount factors of all the individuals involved in the market. So in a way, stochastic discount factor is the market. You can imagine that in the market there exists a certain product in which you can invest without any uncertainty. Like, for example, you go to the bank and say, okay, I would like to open a bank account. What are the rates available? And they say, okay, for example, 1%. So then you know what will be the outcome on the next day, tomorrow. So if there is no uncertainty, the payoff tomorrow connected to the price today by a certain coefficient, RF, F stands for fixed, for example, and that RF is not a random variable. It's a known, it's something which you know. So this equation you can rewrite in the following form. The asset pricing equation is a kind of like generalization, a big generalization of this simple formula. Let's compare that to an asset which is risky. So if I have some risky asset and I use here the index I on top because I would like to indicate that there are many of them. Risky asset 1, risky asset 2, risky asset blah blah blah, risky asset number I, right? So I also can compute the expected value of my payoff, right? And the two, if you want to do some analogy of this formula, the two I can connect by a similar formula where Ri, capital Ri, is something similar to this risk-free rate, but now this is not a constant. Since the asset is risky, this element becomes a random. So what do you think? Suppose these formulas, they can be applied to different types of assets. For example, to stocks, right? If you have a stock, it has a certain price today, P, a certain price, and then some P off. But it also applies to simple bank accounts in which you can put just €1, for example. In that case, your price is like €1. Here €1 and here €1. What do you think will happen? How these two compare to each other? The rate which the fixed rate, which you receive for at the bank, which is known in advance, or the return of some risky asset. What would be the connection between these two? Which one is bigger? Which one is? Well, the risky one is bigger, but actually it depends. It depends on what kind of product it is. So on the next slide, I would like to go and a little bit explore the connection between the two. Now on this slide, from this slide onwards, I'm kind of like dropping this small index t corresponding to the time, just to make formulas more simple. But we still think that there is a kind of like a time variable over there, just to simplify formulas. So this is my asset pricing equation, that super big equation, super valuable equation over there. This is just simple covariance formula from the first chapter of probability theory class. And this is rewriting again that risk-free rate. So if I invest 1 euro in a bank account with a known rate, with that rate which is like published on the bank's bulletin, which is like RF, at the same time, my asset pricing equation should hold. So combining two together, I get this formula. So price 1, I expect to get RF tomorrow. This is not a random variable, so I can factor it out, and I have a nice formula connecting the expectation of this stochastic discount factor and the risk-free rate. Now, if you combine these three together, you can rewrite the asset pricing equation in the following form. Now, let's look at it. What does it say to us now? So the fair price today actually equal to some expected value of payoff, so how much we expect to receive from investment, discounted, because that's going to be tomorrow, right? So we discount by that risk-free rate coefficient, because everyone can put money today and receive 1 euro today and receive RF tomorrow. Let's assume it's positive. And there's another term over here, and that is exactly the term for what we call the risk adjustment term. Let's look at this term. What does it tell us? So this bit over here, erasing that one, that's the price of discounted price. So what will happen if this covariance is negative? The price will be smaller than expected value. If covariance is bigger, then the price is going to be bigger. Let's think a little bit about what does that mean for covariance between m and x to be positive or negative. And in order to do that, maybe I need for a moment to return to the formula for the m. Let's look at this formula over here. And remember this graph for the function u, okay? Now, beta is just some constant. The denominator here is not a random variable. It is known today. Now, u prime of the consumption, that is the source of randomness. Let's now analyze how that expression depends on the consumption. So, if the consumption grows, then derivative, what? Decreases. Okay, consumption grows, stochastic factor decreases. Consumption grows, stochastic factor decreases. Repeating it, okay? Now, coming back to my next slide. Look at this covariance term. So suppose our asset X is some kind of thing which is sort of a fashion thing. So if consumption grows, everyone starts investing in some in something, right? And so our asset also grows with that, right? Then what is the covariance between m and x? M, when consumption grows, does what? Decreases. If your asset is an asset of kind of like a fashion type of asset, which grows when consumption grows, then the two are correlated negatively, because they go the opposite way. So that means that the fair price of such thing will having a negative term here. In other words, it will be priced with some discount. Now, if it is the asset of a very different nature, such as like insurance, insurance protects you when things go bad. So when there's a crisis, insurance protects you. So then, with the growth of consumption, insurance also decreases. And it behaves then in a in the same way as the discount factor. So these two are positively correlated. So this thing is slightly, so you have here a premium which you pay, so insurance premium which you pay to invest in that insurance account, the hedge. You pay for the hedge, but the hedge protects you when things go badly. This type of things, so the asset pricing specialists, they do a lot of conclusions like that from the very simple, from the very basic equation, asset pricing equation. Okay? I would like to do a little bit more rewriting of the formulas to bring you to one topic which I am interested at. Let me start with the risky asset now. So again, let me invest €1 into that risky asset. According to the asset pricing formula, this is the expectation of the product. Then I use that covariance formula again. And then I change expected value of M into 1 over risk-free rate. Okay? So I got this. Now I multiply the first equation by RF and rewrite it in the following way. So here I have the expected return of a risky instrument minus the risk-free rate. What is that? That is, okay, you have option, invest in a risky instrument or just simply put your money in the bank account where you'll get this rate. So this is what is called excess return of a risky asset. It's how much more or less you get by investing in a risky asset. Okay? And that's what it depends on. And it depends on the covariance between M and that Ri. And again, the story is similar. So this covariance, if it is positive, then this whole thing becomes negative, and vice versa. This formula tells us one more story. And that story is that this excess return really depends on that, only on that covariance. So let's think about some risky asset. It might have some behavior which is kind of depending on the whole market behavior. So everyone goes and I go. But that particular risky asset can have something which is completely perpendicular to where market goes. Some sort of a risk which is only of that instrument. This formula tells us that only that part which goes along with the market, only that part contributes to the difference of price. While the part which is kind of like perpendicular to the market doesn't make any contribution to the price equation, although there is a risk associated to that. And that's an important division which is very much similar to how you do projections of vectors in linear algebra. So if you have, like in vector space, one vector which is representing the market, M, and the other vector, which is X, represents our, maybe I can draw this picture over here. So you have your vector X, and then there's a vector M. So that's where the kind of like market points. That's where your risky asset points. The only thing which will actually affect the price will be the projection of X onto M. This projection of X onto M. While the perpendicular component, although it brings a risk, it doesn't contribute to the fair price of the instrument. Okay? So this extra bit, this epsilon over here, perpendicular to the market, covariance equals to 0. Conclusion, that whenever we talk about the return, excess return, of a certain risky instrument, there is always a component which is called systematic component, the projection. And there is a component which is called idiosyncratic or specific. And that is a risk component which is perpendicular to the market. A generic conclusion from that is that whenever you want to think about hedging, you invested in a risky asset. Whenever you want to hedge that investment, the only risk you can hedge is the systematic risk. The idiosyncratic risk, this perpendicular component, cannot be hedged by any other instrument because it's like specific to that particular instrument. All right? So so idea number one was that we have this asset pricing equation. Idea number two is that for a risky asset, there is a systematic component, which is explained by market in general, and then there is a specific component for that particular instrument. Well, that's pretty much it about the pricing asset theory. The rest is, let's try to find and model this magical coefficient m, and if we model this stochastic discount factor, if we come up with certain formula of how we can measure something and then fit a model for that, then we're good. Then we can do the pricing, we can do the risk computations. And there's a big theory about that. It started with the some very simple model, capital asset pricing model by Mr. Sharpe in long time ago, where the stochastic discount factor was simply just said to be a linear combination. The key component here in the linear combination, it was called a wealth portfolio. Think about one of those big indices which are like S&P 500 index or any other big index. If you're talking about like one particular country, that's that country index, FTSE 1100 in UK, for example, or whatever you like. So that was the model, the simplistic model. Then, a couple of years later, people said, well, actually, we better introduce a number of factors. So, a number of factors, FIs, so that our return of the risky portfolio actually is a linear combination of returns of those individual factors plus that idiosyncratic part. I will skip the details because these two, it's like one of those mountains where you can go and climb and consider all the details. And there is a lot of literature about that. And I want to jump quickly, immediately, to the current day story. And current day story is not very much different to this one. So contemporary, like today's story, is that if you have, it's just the same factor story. So today, if you talk about, for example, equities, and you want to invest in world equities or like equities in Europe or any particular country, you have a lot of factor models. A factor model, each of the factor models, would come with a certain collection of factors. Typically, your universe here, capital N, has a different meaning to what originally was in the lecture. Capital N now is the number of potential assets you can invest. Let's talk about equities, for example. The number of European companies you can invest into. How many are there? Thousands, right? 10,000s, 20,000s. Listed on the European exchange. So that's thousands, right? Now, if you really want to deal with them, modeling, analyzing the data for each particular company, that requires too much computation, even with machine learning. So what people come up with is say, okay, fine, let's explain the whole universe of stocks with a few factors. So K here is the number of factors. Depends on model. Everyone can come up with a model. You can create a model with 3 factors. You can say, no, 3 is not enough, 100 factors. But definitely, the number of factors is much, much, much less than the number of instruments. And each factor might have a certain meaning. For example, we can say, okay, factor number 1 is the whole market. Factor number 2 is a certain country, like, for example, France or Germany or Italy. Another group of factors can be about the sectors, what they call them. For example, oil and gas sector, or IT sector, or machinery sector. So each of these Fs here, it's kind of like represent a concept, but at the same time, it is linked to a certain index. Or they might be also factors which are more fancy than that. In any case, you would like, the model says that your return, excess return, above the level of the risk-free rate, can be modeled by those factors plus some idiosyncratic term which is specific for this particular company only. Naturally, you would like to invest with the, and you assume that this idiosyncratic term has 0 covariance with all the factors. This is supposed to be delta as well. So different idiosyncratic returns for different companies also not correlated with each other. Okay? And naturally, you would like to invest not in a single risky asset, but maybe in the whole portfolio of risky assets. So portfolio I represent by index P. And then it becomes like this heavy formulas, which maybe I would like to much cleaner introduce by drawing some pictures. So that's the modern day portfolio. So how it works in practice? In practice, it works like that. Every morning on your doorsteps, you find a package, a parcel, with 3 matrices. So it's matrices B, A, and D. So what are the matrix B? Matrix B is a square symmetric matrix, K by K, which is the factor covariance matrix. So an entry of that matrix gives me a covariance between factor I and factor J, or between factor I and itself. So that's a square matrix. Now, that's square matrix B. I also have a matrix A, which is which looks like that. And that matrix has size K here and N here. This is a matrix that tells me how it's a matrix with those coefficients over here, which tells me how each individual instrument depends on factors. They're called factor exposures or factor loadings. For example, if my factors are countries, sectors, the whole market, then I basically say, okay, let's take a company, whichever, like Tesco. That's a British supermarket. So it is having coefficient 1 to country UK. It's having coefficient 0 to country France. It's having coefficient 1 to sector grocery shops, and it has coefficient 0 to factor oil and gas companies. There are some other factors which are more, which are different. Who defines the factors? The modelers. There are many modelers. There are modelers who sell those matrices to the public, so they basically sell matrices. Or maybe big financial institution can hire some people and say, okay, let's create our own model. And then you think fast, do some machine learning, very, very complicated stuff, and say, bring some factors to the head of that organization, say, oh, we come up with a supermodel, it explains everything, here are our factors. And then the person says, okay, what is your factor number 57? And you say, oh, you know, it's kind of like a machine learning factor 57. It's very hard, it's very complicated, hard to explain. And that person says, no. If you have 57 factors, you have to tell me exactly what that factor means. I understand country, I understand sector, but this machine learning, blah, 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 I don't understand. So there are different models. Sometimes you need to be able to explain what your factors actually mean, right? Okay. Factor can be, for example, factor can be growth. A factor can be size of the company. And then it can be not just 1 and 0, because some companies are big, some companies are small, right? And they differently react to market things. Anyway, so this is the matrix of factor loadings. So it tells me how each, so this is ith row here and j's column here will give me how instrument number j is related to factor number a. And finally, my matrix D, or rather a vector D, is a diagonal matrix with only elements on the diagonal and zeros here. And each entry here will give me the variance of that, should be delta again, of that idiosyncratic part associated with that particular instrument, with that particular company. So, having these three matrices, what you can do, firstly, you combine from them one big matrix. And the way it looks like that. So you have square matrix B, non-square matrix A like that, and A transposed like that. That's why you need to learn linear algebra as well. So if I multiply these matrices together like that, then I get, as a result, a big matrix n by n. N by n, so like 10,000 by 10,000, right? In that matrix, if I add to it my diagonal matrix D, which is also 10,000 by 10,000, but it's diagonal, so it's easy to store in memory of a computer. So I get this matrix sigma. So plus matrix D. So matrix sigma is then the key object of the story, is the covariance matrix of stocks. So the entry of this matrix sigma gives me the covariance of stock E to stock G. Now, if I also have a vector W, that will be our main variable, holdings of our portfolio, then I can multiply my matrix sigma by vector W like that, and multiply by the transposed version of this vector W like that. And what do I get? I get the variance of the whole portfolio. Variance of the portfolio means, in plain terms, how my portfolio what will be the price of my portfolio looking forward tomorrow, in 1 week, in 1 year? How much can it go plus or minus from my current value of the portfolio? How much will it variate, roughly speaking? Okay? Think about it. If W is measured in dollars, or in euros, right? In euros. So each component of the vector W is how many euros you invested in a particular stock. Then, what will be the unit of this expression? So I multiply, this is the covariance matrix, it doesn't have any units. This is euros, nothing, euros. So what's the result is? Squared euros. So you come to the boss and say, hey, we find a model, you know, our risk is 10,000 square dollars. He says, what? Well, what do you mean by square dollars? The dollars are not square. Oh, euros are not square, they're like rectangular. So that doesn't work, right? So you cannot do square euros with people. So you have to take the square root of that. And that is then the risk of the portfolio. Okay, so that is the contemporary state. That's what people do today. So what exactly, how they use that? What kind of problems do they solve? Okay, here's what kind of problems when they solve. They solve, let me skip this for a while. They solve the following type of problems. That expression, or rather the square root of that, was about the risk of the portfolio. We also have some vector of stock level return signals. Signals is what the other department of our company brings to us. The guys working in those departments, they do some very fancy machine learning stuff to come up with a vector of what they call alphas. Alpha is basically a prediction of where the price of the return for tomorrow. So alpha gives me, if I multiply alpha by my vector w, it gives me the expected return of my portfolio. The expression which we just discussed over here, this square root, gives me the risk of my portfolio. So I have these two most important things, the expected return and the risk. And I have to balance them. And here are the three classical problems. How do you balance them in a everyday portfolio management? First two problems are simple, and the third one is a combination of the two. Problem number one. Suppose you are given a certain level of risk. Your manager says you do whatever you want, but the risk must be below this level. And you say, okay, fine. So we need to maximize alpha times our portfolio, but keeping the that square root expression under control. The other way around, you can say, or that manager can say, our target return for this quarter is this. Then the problem would be, let's reach that target, if possible, of course, but trying to minimize the risk. In that case, you will minimize the risk of that expression, which is that, that square root of that quadratic term, under the condition that under this linear inequality condition, that your returns are bigger than the fixed value. And combining these two together in a kind of utility function which has both components, which has the return component and the risk component, you have what is called the Markowitz. Markowitz is the guy who received the Nobel Prize for economics for exactly this in some 50. The original work was 50-something, 1950-something, but Nobel Prize was about 30 or 40 years later. Typical. Where you combine the return term and the risk term. And you see, I write it here as a minimization problem. So I'm minimizing negative returns, meaning I'm maximizing returns. And in order to balance these two terms, I put some coefficient lambda here, which is called the risk aversion factor. Again, this is something which is very hard to measure, but it is a kind of like, how much do I like risk? If lambda is 0, then our problem number 3 simply becomes a problem number 1 without this condition. If, on the contrary, lambda goes to infinity, it becomes a kind of like a problem 2. So anything in between 0 and plus infinity is, well, we'll see what happens actually over there. One more typical condition is that E here, again, different to the previous notation, is just simply the vector of all ones. So this condition over here says sum of all my weights in my portfolio equal still to that €1 which I have and I want to invest in the most optimal way. So these are the three classical problems, and these three classical problems we are solved on some toy example in that Python notebook to which we will go shortly. But before we go there, just very quickly, here, next one. Very quickly, I don't want to go into all the details of this slide, but on the previous slide, we had what is called portfolio selection problem. I have my euro, I want to invest it in something, right? But if you think about an organization which already has some investments, then you have some portfolio management problem, which means you have some existing portfolio, W, and you want to rebalance it. Things change, situation change, you need to add something to this W to make a new portfolio, new optimal portfolio. And in that case, you have, again, the risk term, the term which corresponds to the expected returns of the portfolio. But you also have one more term. If you want to rebalance that portfolio, then you probably need to sell something and then to buy something. But that operation of selling and buying on the market is not cost-free. There is a cost associated to that, which is called the transaction cost. Some different models of transaction costs. It's again a special topic. I have some in that notebook at the end in the homework section. And you might have some constraints. So not just simple utility function, go on, minimize. But you also have some constraints. Don't invest too much in that sector. Don't invest too much in that country. Or actually, the difference in things we invested in France minus the things we invested to Germany, but be smaller than 2 times of what we invested to Italy. Why? Managers' decisions. But they might come with those constraints, right? And you need to write up something which satisfies them. Write something where, using what? All these problems, they fit into the class of conic optimization problems. So what is a conic optimization problem? So linear optimization problem is when everything is linear, utility function is linear, constraints are linear, and you know that there's a whole theory about like algorithms that do that. Now, quadratic problems with the parabolas, we all remember how to solve quadratic equations. That also seems to be more or less okay. But having our discussion about quadratic dollars, we understand that we need to take the square roots of the quadratic function. And when you take a square root of a quadratic function, if you have a function x squared, right, and you take a square of that, what do you get? You get a function that looks like this, right? What if you have 2 variables? What kind of function is that? Well, if my third variable is over here, this is x, this is y, and this is function z. So what kind of? It becomes a cone. Okay? So if you have constraints which look like that, or actually, sorry, big or equal, which look like that. So if your optimization problem has linear pieces, like, for example, this looks like the alpha t times w, right? And if you have a constraint that a certain variable, look at this second equation over here. You might have some linear constraints. That is simple linear constraint. That's matrix times vector equals to vector. This one over here, if I rewrite it as s equal to gx minus, s equals to h minus gx, right? Like that. And then there's a constraint over here that X belongs to, all these guys are cones. So S belongs to a cone. So this is a linear combination. S belongs to a cone. That means that S, like on my picture over here, lies somewhere within that cone. So this is the constraint of the following type. S is a vector. S lies within the cone. Let's, for example, over here. That means that the third component of this cone is bigger or equal than the square root of the sum of the squares of the first two components. That is a conic optimization problem. If you manage somehow to write up your problem into this conic formulation, then it turns out that, look at the primal problem of here. I won't discuss the dual problem. So if you manage to write your problem in this way, so X is your vector of variables. Think about our investments in different asset stocks. So whatever we're maximizing is a linear combination. Now, also the last one is a linear relation. Relation with G0, S0, and H0. The constraint here is that these S's, they're called slack variables. Slack variables means that you add this variable, they don't mean anything. They are supporting variables for your optimization problems. They are kind of dummy variables that help you to write the problem in a way so that your super optimizer can actually solve it. So this constraint, in other words, we're written up as a certain combination, linear combination of G0x and H0 is bigger or equal than 0. It's a simplistic version of cone. It's a cone in one dimension. Now, the second constraint, and again, there might be many of them, but if you just look at it, again, this slack variable, where the first component is bigger or equal than the norm of all the other components, is exactly this type of relation. So the task is then to use somehow rewrite the problem, that Markowitz optimization problem, in this form, because this is the form our CVXOPT package can understand. And now we're reaching to the third part of our lecture, which is like the practical. Okay, so how are we going to do that practically? So what I'm using from, it's Python, but of course these optimizers exist in any language you like. C++, of course, is used for really good cases. So I'm using just NumPy because I will need to do a little bit of linear algebra. And I use CVXOPT mostly and Matplotlib just to draw pictures. Nothing else. Okay? I will have my funny portfolio with 4 assets, which are called Ant, Bee, Croc, and Dino. This will be my matrix A, my matrix B, and my matrix D. Again, let's assume that I've subscribed, I purchased that service, that some guys who know how to analyze data, they produce these matrices based on the past observations, based on some tricky ideas, also maybe asking maybe simply ChatGPT, please give me the matrices. I don't know, but they give it to me, and let's say we believe them for now. So we combine this fancy covariance matrix, and here in my CVXOPT packages, I can just simply multiply matrices like that. In order to deal with the square roots, I need a piece from linear algebra that any symmetric matrix, I can actually take a square root of that. It's called the Cholesky decomposition. Fancy linear algebra. If there will be a linear algebra class, you can ask the teacher to show you how this is done. But the result is that this sigma is simply becomes a product of 2 matrices. Okay? So this computes, that's why I need NumPy, because it computes me, it's a linear alg package in NumPy computes that Cholesky decomposition. And you see that this Cholesky decomposition is an upper triangular matrix. So all the under diagonal elements are 0. So it's upper triangular. All right? Very good. Now let's do some sample portfolio. As I said, let me have, okay, not €1. €1 is not fun. 1 million euro. Okay? And suppose I have some ideas from my quants, that my quants, they say, all right, this is how you should invest it. You should invest it like 20% in the AND, 25% into B, 30%, which is some random portfolio. Altogether, these are weights, right? Altogether, these weights are equal 1. So my full million invested. So let me compute these things, this square root, this variance, and the risk, which is the square root of that. And that gives me the number. So I don't specify what time I'm looking at, whether it's investment for 1 day, for 1 week, for 1 year. But let's think about some, let's say 1 day for simplicity, but it actually can be, it depends on the scaling. So what does it mean? What does it mean? My risk is 39,000, 40,000. It means that I have my million invested, but it can go plus minus 40,000 over the next period, right? Okay, good. That's my risk. Here I'm checking that my that this linear algebra piece is actually working, that Cholesky decomposition is working, that instead of taking the square root function, I can actually apply my square root matrix to my portfolio, take the norm of that, that's the norm of the vector, basically squares of all the components, and that I give the same thing. It means checking that the linear algebra works. All right, now again from the quants, suppose quants tell me that, you know what, AND will grow 1%, B 2%, what was the third one? Croc will go 3%, and Adina will go 4%. I said, wow, that's nice. Let me compute then return of my portfolio, expected return of my portfolio, and that's 30,000. Again, this is a little bit artificial example, so our risk and return are on the same scale. 40,000 of risk, 30,000 of return. So, but on this example, as you'll see later on, the pictures will be nicer. So I'm expected to realize 30,000 plus minus 40,000 of the risk, right? Okay, let's go over optimization problem number 1. That's maximizing the expected return for a given level of risk. So I go to my compliance department and say, okay, how much risk can we take? And they come back to me and say, no more than 36. 36 is at maximal. I say, fine, here is my maximal risk, 36. Then my original portfolio doesn't work, because the risk there is 40, right? I need some other reallocation of assets. So what I do my conic formulation over here, and that is how CVXOPT understands my problem, conic problem. So I need to formulate somehow the question about minimal risk into this setup. Well, let's see what will be what. So firstly, I will start with this constraint about the linear inequality, this one over here. I will introduce what my vector will be. What will be this vector x? This is not it is not just the same as vector of my portfolio, because I will need one more variable to add to it. I will need a variable r that represents the risk of my so the vector which I put into the optimization problem will be like that. So this is the variable r, a dummy variable that represents the whole risk of the portfolio. And these are my investments in N, B, Croc, and Dina. Okay? So the first inequality, the first S0 conditions, I will just simply use those conditions to represent the fact that my investments should be positive, meaning each of these numbers should be positive. And also the fact that this first component, which represents the whole risk of the portfolio, should be less than the 36,000. And that's how I'm going to do that. And let me look at, let me tell you how I'm going to do that. I'm going to say that my S0, which is this vector, this is H0 minus matrix G0 multiplied by this vector. So my matrix G0 is over here. Observe that it has here 1 and minus 1, and then all minuses on the diagonal. So it is 1, 0, minus 1, 0, and then 0 here, and on the diagonal minus 1. And my vector H0 is 36 over here, 36,000, and all zeros underneath. So let's do some linear algebra. What is the top, if I multiply, take the top line over here, the equation that corresponds to the top line of matrix G0? It will be 36,000 from here, minus 1 multiplied by R, minus R. And that is the first component of S0. And the condition is that S0 must be positive. So this thing is bigger or equal to 0. What does that mean? That means that my risk is bounded by this number. Next condition. I have 0 here and minus 1. So it's 0 minus minus 1 plus R bigger or equal to 0. And all the other conditions, they look like 0 plus W1 bigger or equal to 0. 0 plus W4 bigger or equal to 0. So that slack variable S0 gives me the constraint that my risk is bounded and all my investments are positive. The slack variable S1, and that's where the conic comes into play, tells me that my risk, this risk variable over here, will actually be bigger or equal than the norm of that square root of the covariance matrix. So this condition encodes the fact that the variable R which I introduce exceeds the actual risk of the portfolio. But since my variable R is bounded by 3060, that will be, combining these two, that will be conditioned that this expression over here is less or equal than 36,000. So I put in my matrix G1, I put here that Cholesky decomposition, that matrix G. I put here minus 1 simply to connect it to R. And my vector H1 is completely 0. Okay? Does it work? And finally, my linear constraint over here is simply saying that my portfolio is fully invested. So I add up all the W1 plus W2 plus W3 plus W4, and I say that altogether that should be 1 million. Because I want fully invested portfolio. And my utility function is the function of those alphas, which quants tell me. So I'm 0 because I want 0 to be multiplied by my R variable. My utility only has to be why they are all negative, because I'm solving minimization problem, minimize. That's why I'm putting negative signs. Minimizing negative returns, meaning maximizing the returns. This is the call of the CVXOPT key function, second order conic programming. And you basically give, in a given order, all the components which we discussed, all those matrices which we discussed. And it's supposed to tell me if it will work. It's supposed to tell me that a separate story is how to write the optimization. It's a completely different subject, how to actually the optimization works. And that's where a lot of math, cool, fancy math, can be done, including the calculus and many other things, and machine learning, of course. So in 8 steps, it does it in steps, shows you all the details. Optimal solution find. So what I'm doing next, I'm checking my optimal solution, taking the a little bit of checks on that. So I'm checking that summing from the 4 elements that I need, that actually gives me 1 million invested, right? And let me compute what is the resulting return and the risk. So the first component is the risk, less than 36. Bingo. What is the return? Well, not so nice, 27, but the risk was the important factor. And I can draw and compare this. So this is simply the diagram. Yellow ones were the original portfolio. The red ones is the optimal number 1. So you bring that to your boss and say, okay, that's how we need to invest. And the boss says, no, let's go the other way around. Let's go minimize the risk for the expected value of return. We cannot return less than 35. Less than 35 is absolutely cannot be done. So we're ready to increase the risk a little bit. So what is the minimal risk for the return 35? And you do a little bit of reformulation, but you're using the same story. S1, the conic condition stays the same. It's absolutely the same, because that's basically relating variable r to the vector. You rewrite a little bit the condition about your, you rewrite the utility function. Now your utility function becomes simply that variable r. So utility function coefficient is 1 and all zeros. And you rearrange the matrices a little bit, and you get the solution. And let's just quickly go through it and look at the picture. And the picture shows you that, well, you need to arrange the portfolio in a different way. And what you can do, and finally, if you want to do it in a more proper way, you can come up with a function that actually takes that risk aversion parameter and computes all these steps and returns the solution for every particular value of risk aversion parameter. I won't try to compute it because we might lose the connection. But here is the, you can take a range of those risk aversion parameters. I've chosen here from 0.1 to 10 logarithmic scale several values. And I run it, and actually I put them all on the plot. And what happens is that you can think that every dot on this line represents an optimal portfolio in a sense. So that was the optimal portfolio when you say we should not go risk over 36. This is the optimal portfolio when you say, on the other hand, your return should be bigger than certain thing. This is the original portfolio, which is below this line, so it is suboptimal in all the sense. So this is the risk, this is the return. Obviously, you cannot have a lot of return with minimal risk. So this is called the efficient frontier, which you cannot go into that region. So if you want more returns, you need to take more risk. On this frontier, every point is an optimal trade-off between the risk and return. Optimal in what sense? In a sense of your risk aversion factor. Your risk aversion factor is basically a slope of the line. You draw a line here with a certain slope, like for example like that, and you draw a set of parallel lines, and whenever it touches this efficient frontier, that's your optimal portfolio corresponding to your risk aversion. This is the picture which you nicely build into a certain software package, and you go and present it to your boss of the company, and they're supposed to be happy and start investing. That's the end of the story. Thank you very much.